Good morning, everyone. So welcome to this second day of this course about the new challenges of the planning of distribution and transmission system, considering the electrification of new energy demand. And today, the first talk of this morning is going to be done by Florin Capitanescu. Florin received the electrical power engineering degree from the University of Polytechnica of Bucharest in 1997, and the PhD from the University of Liège in 2003. And since 2015, he has been leading research at the LIS, the Luxembourg Institute of Science and Technology. His main research interests include the application of mathematical optimization methods to operation of transmission and active distribution systems based on optimal forward flow approaches, power system security, voltage stability, the cost of flexibility, TSO-DSO coordination, cascading outage simulation, and smart sustainable buildings. He has published a lot of transaction papers, and he has served as editor in many IEEE transaction journals like Power Systems, Sustainable Energy, and Smart Grid. And by the way, he serves as well this year as the head of the Power System Computation Conference, and we are quite grateful for that. He's associate senior member of the IEEE. So he's really a specialist on the planning and control of power systems, and today he is going to talk about how to deal with massive penetration of power converters, taking into account the reactive power reserve scarcity in the volt-var problem. So, Florin, it is real pleasure to host you online today here in Seville. So the floor is yours.
Yeah, thank you very much, Jose Maria and Antonio Gomez for the invitation, for the kind invitation. So I visited Seville a couple of times, and it's an outstanding city and also with outstanding researchers. Fortunately, today I could not make it, so I will be only online. So thanks a lot for the nice introduction as well. So let's go to a topic that people didn't talk that much until, let's say, the unfortunate events in April in Spain and Portugal. So reactive power, okay, reactive power reserves, and also at the very end of the presentation, I will give some thoughts about volt-var problem. But everything that I'm going to say relates to how we are going to control voltages through reactive power, okay? From planning to operation. So let me see if this works. So first, some acknowledgement. So what I'm going to present, it's a mixed bag of work that I did with people here in Luxembourg, and we are grateful to the funding from our funding agency, FNR Luxembourg, in some projects. Also, there will be some personal efforts in which I worked alone, so you will see this later, okay? So let's go a bit to the outline of the presentation. So first I will remind a bit of the energy transition, okay? What I mean by this. Then I will give some hints about motivation of this work, why I'm addressing reactive power, what I believe that this deserves to be researched, okay? And I will go into two main research questions. First, how we could identify when reactive power would become scarce, okay? So shortage of reactive power reserves in a power system, a transmission level. I will have a methodology. I will present some methodology based on security constraint optimal power flow. So security here is related to contingencies, okay? So disconnection of lines, generators, transformer, in general, N-1, as is done today, okay? Then, once we identify this, I will talk about how we could alleviate this scarcity, reactive power scarcity. So basically, it's where to install sources to compensate reactive power. Like I'm going to explain how we were thinking to rethink the VAR planning problem, okay? Then I'm going into something which it's, let's say, very hot topic. It's how TSO and DSO could coordinate to control voltages, okay? And also is related to something to the unfortunate events that occurred in Spain, in Portugal. Then associated to this is the idea of how much would cost to procure reactive power from distribution system by the transmission system operator, and we'll end up just with some consideration on future volt-var control. Okay, so let's go into energy transition. So you know that we are in plenty energy transition, and this basically consists in phasing out, let's say, fossil fuel based conventional generators, which mostly were connected to transmission system, and to replace this by renewable sources like wind in transmission, but also plenty of wind and solar in distribution system operator. Okay, so during this transition, we would like to go ideally to 100% renewable if possible. My feeling is that it will not be possible or feasible or economically feasible or in any way, but okay, let's try to see how far we will manage to go by 2050. And you know very well that in the past it was quite boring to operate our power system. With conventional power plants, you can do pretty much everything. You can plan, schedule, everything was, let's say, easy to forecast and foresee. But with renewable, they are small, intermittent, they are many, and they don't have ramp-up capability like for wind. They are dispatchable down. You can only curtail basically, unless you would like to operate deloaded. Same for solar. I would say it's maybe easier overall to predict solar. Again, no ramp up. And the worst thing, it's also that, you know, when let's say my main focus is controlling voltages at transmission level through reactive power dispatch. And the biggest issue that you have plenty of these generators, you know, distributed energy resources that are connected in the distribution system, and they are not visible to the TSO. So the TSO can take actions to believing that improves voltages in transmission, but that may harm distribution. Okay, so the context going on, there are plenty of challenges, right? Because all these renewable energy sources, they are interfaced through, you know, the story, inverter based resources, interface through power electronics converters to the power system. Now plenty of research is, you know, in let's say low inertia. Obviously we may face frequency issues like rate of change that could, the frequency after a contingency could drop very fast or could drop very low. So it's rate of change of frequency, nadir of frequency, and so on. So there are plenty of works on this, but there are also simple technological solution to deal with that. Like, but okay, you can install, for instance, plenty of synchronous condenser in your system. Okay, if you have enough space in substations. Related issue, active power this time again is short circuit currents. You know that all these power electronics have limited capability to provide short circuit current under fault, and that affects strongly the proper operation of protection relays. Okay, this we have a little bit less research on that, but okay, there are some people who came up with new things and new terms, like for something that I don't like that much, associated in system strength, you know, that start now to, you know, look in a different way to power system and try to see how much strength is in the system. And yeah, unfortunately, it's mostly associated with only with short circuit power. However, and this is something that I really like, so I say, okay, when I started this research more than 5 years ago, I say, okay, there is no point to go into these active power issues. There are excellent researchers working on that, but I was surprised. In reactive power, almost nobody has worked at that time, you know. And I see, how is that possible, you know, because if you are unable to have enough reactive power in the system and to control it properly, to control voltage, you cannot transmit reactive power. So, you know, the system may fail also due to scarcity and shortage of reactive power. So, and then I started doing research that again on that topic. First, I did that alone. So, as I said, I started 6 years ago. I said, why this reactive power reserve would be an issue? I was wondering myself, and then I started, you know, analyzing things. And I see first, the most important thing I think is that the renewables that we, you know, that are connected to the system, big quantity, cannot ensure the same high quality of reactive power ancillary services like conventional power plants. That's the big thing. Let's take it one by one. Okay, you have renewables at transmission. Well, for conventional power plants, in the past, they were planned at appropriate location to face predictable operating conditions, right? Now this is completely uncoordinated. We have in Europe plenty of wind that is connected in, let's say, North Sea, or solar in, I don't know, in the south of Europe, but not necessarily close to the biggest load, for instance. Or another issue is that reactive power, as you know, cannot travel far. Active power you can transfer maybe from Portugal to Ukraine and vice versa, but reactive power is quite local. So it's very important when you put it. So for that reason, all this wind generation that we have, you can have tons of gigawatts of power and gigawatt. They will not travel until from North Sea until I don't know, Madrid or whomever, even Brussels or below to Luxembourg to us. Okay, so it's very, very important how we plan that. Another thing is, if you take a, let's say, at the same rated power, a conventional generator and let's say inverter based resource, you will see that they are constructed in a way in which their capability is smaller actually, and quite smaller, especially on absorption mode. Okay, so neither production nor absorption of reactive power. So another issue is, as I said, due to intermittency and variability of power flows, active and reactive, through the networks with plenty of renewables, that will create stress in unforeseen situation and where reserves are scarce. Okay. Another big issue with renewables is that nobody knows, the model, and the operators don't know. And sometimes we already saw they may disconnect, even though on principle, they should follow the fault right through capability and grid code, whatever. In practice, when you want them to stay connected, they don't. Like, for instance, when you have more unusual operating conditions, it happened in Australia, 2016, they are at the origin of a blackout. In 2019, in UK, again, they contributed, they disconnected when some nasty transients. Again, they should have stayed connected, and then they recognized, the owner, that there was a bug in the software, whatever. Even I don't know exactly what happened in Spain. I didn't follow the full sequence of events. That might have been also, I don't know. It could be, but this is something very, very bad actually. So now we have also plenty, as I said, of inverter-based resources as distribution system. However, I think this is good in principle because it's next to the load, so to some extent, they decrease losses. But on the other hand, there are issues with that because we cannot use them properly for the whole system. Most of them, by grid code, they operate at unitary power factor. You cannot control that much. There are plenty of PV panels, on rooftop of houses, and you cannot send a crew there to, I don't know, to change for every inverter, to provide new settings, or to send them remotely settings or things like that. So this is quite ineffective actually. And in addition, in general, due to low investment in distribution system, you may have voltage issues, you may have local congestion, so you cannot push that much reactive power from lower voltages, low voltage to medium voltage, to support transmission system. Okay, you have also stages of transformers. Anyway, so I think that you might have been to some extent convinced of it makes really sense to look very closely at these reactive power issues. Another important point, and this is actually a positive of distributed energy resources, even if they don't produce active power, they are still connected to the grid, they may produce reactive power. However, for now, they are not incentivized to do so. Okay. So that's something that could change. Okay, so based on all of these things that are, my thoughts on, reactive power issues. Again, I published a paper in 2020. It was in Power System Computation Conference, when I say, okay, in this condition, the transmission grid will face situation of lack of excess of reactive power. Okay. And for that reason, we need really to see when this situation could occur, what I called breaking point. So when during this energy transition, or given penetration of renewables, for instance, reactive power will become scarce. And I developed the very first crude methodology to let's say, proof of concept for this issue in that work. Okay. So basically what I was looking, so I was formulating AC security constraint OPF in both reactive power production mode and reactive power absorption mode. So this is formulation just for production mode. When I define a new variable, which is, let's say, the reactive power reserve that it's absolutely needed. And then I'm trying to look into the system when trying to satisfy the set of operating constraints like power flow equations, active, reactive power, currents in the system, and voltages, especially given active and reactive power limits. For all contingency, normal operation and other contingency, I was trying to see what is the minimum needed reactive power reserves, okay, in the system. So then I started stressing the system, okay, by taking generators, so simulating phasing out of synchronous generator and replacement by renewables, until at some point this problem doesn't converge, so you don't have any more reactive power. To avoid these issues, I defined also here, I relaxed a bit this balance of reactive power and I penalize it here in the objective function. So just to realize, okay, if it's really, it's a numerical infeasibility, and to make sure that it's not, that the problem is really infeasible. So it's the point where we start needing adding reactive power into the system, okay? So basically the methodology, that's very easy, as I even could not call it really methodology, but okay, I took 2 points basically for energy transition. So I say, okay, I disconnect one generator and then I compensate in a way his megawatt and megavar plant. And then I look at the peak load and light load that correspond also to reactive power in production mode and light load in absorption mode to see how much it can capture. And for each of them, I solve that problem. If everything is fine, so I solve this problem here for production and this is not infeasible, so I go back to then, I keep removing, simulating phasing out of conventional generators and again, increasing penetration of renewables until I get infeasible. And then I say, okay, well, when I get infeasible, it means that I reached my breaking point, okay? So now the energy transition scenario, okay, don't laugh, but it was very easy. So again, remove one generator from service, and it was also in a conservative way. I did this in a conservative way. So I compensate active and reactive power, like for power injection at the same node coming, assuming that it comes from distribution system. And again, I consider unity power factor because it's a conservative assertion. It's good for the TSO because the TSO has to control voltages regardless what the DSO is doing. Okay, I tried then to test it in 2 small systems, so 5 bus system under 6 n minus 1 contingency, system from, let's say, replica of Nordic power system in Europe, 60 nodes, 33 n minus 1 contingencies, okay? Only line trippings this time. So for the 6 nodes, okay, so basically what I'm saying, I take out first this generator and replace with renewables here, then I take out these generators. Obviously, when you take these 2 things out, you remain with only 1 generator, and here you can see the voltages in absorption node, that all voltages drop and drop below all 0.9, okay, in this node here, which is the farther away from G5, you have bad voltages already, so it's the time where the operator should start thinking about, improving the reactive power. Now, on over voltage issue, so again, at light load, you see that once you start losing voltage control, so you don't have any more this generator, so voltage plans start to rise, right? Maybe it resembles a bit what happened in Spain, so you get already over voltages here, where, again, some inverters may disconnect, okay? The same things I did for the other system, so this is a bit, let's say, energy transition scenario where I have here the number of generators that I took out, I phased out. So 1, 2, this is the sequence, okay, until the 5th, the 7th, because after that, the system cannot, the remaining generators cannot support any more voltages properly. So when I look into overall needed reactive power reserves, I represent here as a function of generators, additional generator phased out. So in the base case, you see, I need only, let's say, 1.4 gigavar to maintain the system. Now, also you can criticize because in that case I simply add on megawatts across the system, which obviously it's if you add up megawatts, it's easier, but with megawatt you need to be more careful. But okay, it's an assumption that you can criticize. Then I take one generator out, a second one, and so on until when I disconnect this G7, again, the problem becomes infeasible. You cannot control anymore the voltages properly within limits, okay? Then at the solution of that, what is very important is that actually it gives you how much of the physical reactive power reserves is effective actually, and should receive remuneration, because for instance in one generator you may have, like for instance in G14, okay, you may have it even absorbs reactive power, but then it responds to contingency of that. This is the maximum that it gives across all contingencies at my optimum solution. So basically these orange areas are what is effective of auto generators, but obviously this is only part of their physical capability. So the other is useless because basically it cannot help anymore to control voltages. Your system is already experienced low voltages, and maybe it may go into a voltage instability. Okay, so that's another interesting concept, the concept of effective reactive power reserve. Then this shows a bit like when I phasing out those generators with different colors here, how these effective reserves are, reacting. And obviously, in most of the case, so for most generators, they are slightly increasing, as you can see here, but not always, because in some cases, it depends on the specific network situation. It may also have an opposite view, okay? So that was about, let's say, what I did alone 5 years ago in the papers published 5 years ago. Since then, so we started as a team, okay, with my colleagues here, Elnaz and Louis from Louis Wenkel from Liège. So in another project, we say, okay, let's do some sophisticated and do a proper comprehensive methodology to address this, because what I did there, it was just, let's say, proof of concept, a simple exercise. And then we started looking at the problem, and we developed proper modules, computational modules to take this. Basically, in our methodology, we have 4 main computational modules. I will explain later. So it's a conventional AC security constraint OPF. Then there is a version of it to calculate overall needed reserves in a production mode, another one in absorption mode. And at the end of the day, it's optimal reactive power dispatch, okay, through security constraint OPF. So you can refer to the paper for the full methodology. So this is the full methodology, and probably you cannot even see it very well from where you are. Again, we have at the input from the energy transition, we have forecasted load profiles, let's say a big mutation and transformation in a power system, like which conventional power plant will be phased out at what time and how this will be compensated with renewables. Then we go into, let's say, 1 year ahead operation with this data. And again, we have a forecast of renewables through ARIMA models, topology of the system, load profiles. And then we go for some representative days. We picked kind of 8 days from what I remember. And for each of the day, then we generate some RES scenarios, so a number of, to simulate uncertainty in RES production. Then we go for all 24 hours, and we solve first an AC security constraint OPF. And then we calculate in production and absorption mode how much reactive power reserves we need. Okay, and at the end of the day, we obtain a distribution of RPRs. Sometimes we may get feasibility problem, and then we see to what extent, let's say, the optimal redispatch of reactive power could support that. I think that you could look into the paper to that. It's quite tricky. But okay, I will show maybe it's easier to understand from the results sometimes. So if I'm looking, let's say, typical summer work day, so I have the 24 hours. So again, for each hour, you have kind of 10 scenario, and this represents the overall reactive power reserves in gigawatt. So this is where all generators are there. Once I take one generator out, okay, it increases a bit to some extent. I take the second generator out, we see here that we have some infeasibility. So these scenarios, the grid already cannot cope with second generator out, okay? Then if I keep going, you see that pretty much all scenarios, so pretty much all the time of the day, I cannot keep the voltage. Once I take the G7 out, so absolutely all scenario, all times of the day, you cannot maintain voltage profile. And then just to show a bit how much optimal reactive power reserves could, redispatch could support. So in that case, if you look at these 2 diagrams, so it shows that in some cases, like for instance, in some hours here or here, it's able still to control voltages if you are able to do volt-var properly, okay, volt-var control, but it will not solve all issues. But now, obviously, if we would have applied it early in the stage optimal reactive power dispatch, that could solve the problems, okay? Now, in absorption mode, same story. So again, you see that it's not that much in absorption. So the same sequence of generators doesn't change that much. Here we started having issues in absorptions the same time, here also, and again the ORPD. So I think that they look a bit similar, just the numbers are a bit different. So again, you can do with redispatching reactive power can help a bit, but cannot solve everything. So at some point you will need to plan these things out. Now, in the methodology, as I said, is comprehensive, and you need to think a lot about a lot of things. So for instance, how to compensate the megawatt when you phase out generators, where will be installed actually these reactive power resources. So we have two variants here. So one, we say, okay, very rough stuff. We have let's say at the same node RES at unitary power factor. In the other, we look at across the system. We have a let's say a proportional distribution across the system if we don't know with exactly where that could happen. And you can see again, as you, for instance, in production mode for RPRs, that when you disconnect G7, you already, you know, with one of the variant one, you get there, but with second variant, actually you get to, you are able to keep to still be feasible with G7. So it will go a little bit later. Okay, so just a way to say that many assumptions have a role. Now, if you look, it's very interesting in absorption mode, and I didn't know that, but it's very strange. You see that absorption mode, actually, it's much more constraining. Issues occur immediately after you have the second generator out. You in both cases, you have already issues. So basically, you cannot control over voltages, which is very interesting, actually. And then also what happened in Spain and Portugal, it was also actually, you know, an issue of over voltages. In the past, people were crazy with under voltages and voltage collapse, but this, it was the other way around. And even very funny, these results show, let's say, well ahead of the time that actually we don't have enough we may not have enough absorption capability for reactive power in our system. So it poses more problem that, you know, what used to pose problem in the past. Okay, then when we look at how you initialize, because obviously when you simulate these days, you need to simulate some optimal reaction of operator. So if you have just power flows, you see that basically you get infeasibility when you phase out G19. But if you look at security constraint OPF, you see that you need first less reserves. So this would be like the operator should react maybe, but you can also postpone a bit the moment where you start having issues, okay, with reactive power. Again, if you look in absorption mode of reactive power reserves, the same story with power flow. You get immediately. So once you phase out G16 and for anything that follows, everything is in red, so everything is infeasible. But if you still manage properly, let's say the dispatch in day ahead, so you see that you can postpone quite a lot. So these issues of reactive power in absorption occur later on. So again, very important how you set and how you have your assumption. Now, obviously, these are, let's say, so security constraint OPF, it's still planning, but okay, people are, okay, what is the largest problem you can solve and how much time it takes? So basically the largest problem, so we tested for a system that, you know, European system of 1,200 nodes, and basically with different set of contingencies, increasing contingency up to 20. So you can see obviously the reactive power reserve in production and absorption mode keep increasing in both cases. Also the computation time, but still this is for a single problem. So again, when you run the methodology, you will solve maybe a couple of times this problem. So, but again, the slowest problem you solve in 5 minutes. That means that, you know, you may solve this 20 times, so it's still doable at planning stage. You can do plenty of things with that. Okay, so I think that was nice to see how we can identify when the scarcity of reactive power reserves could occur. Okay, and these are some conclusions. I will share the slides. We do anyway later for those who wants just ask Jose Maria. Again, at the core, we have 4 tailored computation block based on security. So n-1 constraint optimal power flow. This is non-convex, non-linear. So you have guarantee only for local optimum, but in general, it provides also the global optimum, empirical evidence in power system. So I think this could be a good decision support tool for operator to plug and play different energy transition scenario, also to see when, you know, in also different times of the day. But also it's a good for grid planners to see the timing for reinforcing the reactive power support and also which are the related hotspots in the area. And following up this point, we moved into, okay, once we know pretty much where the bad things could happen in terms of voltage control and reactive power scarcity, let's see how we can counteract this. So we moved into reactive power planning problem, okay? So we say, okay, this we need to rethink from scratch because, you know, people were working on that, I don't know, 20 years ago or maybe 10 years ago, but there were not much renewables, not kind of technologies that we have today. So again, you can refer to that IEEE transaction power system paper that it's in early access about our, let's say, scalable methodology to mitigate reactive power scarcity, okay, during energy transition. So what is it about this VAR planning problem? So VAR planning, it's basically where in the system, how much and which technology you would deploy to, let's say, to keep up with voltages, to maintain voltages thanks to reactive power dispatch, right? So you have these classical static VAR sources like shunt, capacitor, reactor banks, but you have also dynamic things like synchronous condensers, STATCOMs, SVCs, okay? Now, what is the interesting thing and where the issues in the energy transition of reactive and active power join together is that some of these, especially STATCOMs and synchronous condenser, contribute to much more than reactive power. In the past, for instance, you have synchronous condenser, which was the let's say the paria of the power system that was used just to control voltages if you don't want to do something else. Now it contributes to many things. It provides inertia. It provides also contributes to short circuit current. So it's for me a silver bullet that you need to be really exploited by operators. Some are already doing it. I think in Italy they buy and they are deploying, and so Terna. I think it's a very good idea. Then we have also IBRs that have, as I said, different power capability. But again, we need also to look more and more to DSOs because the power flows are now, in the past, there were in one single quadrant. Let's say power were flowing active and reactive from TSO to DSO. Now we have almost 4 operation quadrants. You can see pretty much in some countries, pretty much everything at the interface between TSO and DSO. Good. So again, we developed a methodology. Again, we need to be security constrained because the transmission system operators need in practice to cope with N-1 security in a way or another. So we did a sort of develop a stochastic multi-period OPF. So basically by stochastic, I mean that we take into account stochasticity of renewable energy production, okay? Multi-period, it means that it covers the whole day, okay? And obviously several days in your planning problem. But again, the issue is you get into very, very nasty mixed integer nonlinear programming problem that no solver can tackle for a real system, okay? Because this is, you cannot get worse in power system that these mean LP problems. So it's a big computational problem. However, there is also something very nice with reactive power that some people do not think about even, is that it's quasi instantaneous. So it doesn't have time coupling. So in active power, yes, you have a lot of time coupling, not only in the past with generators that you solve unit commitment, that they have their obviously physical constraints to ramp up and ramp down. Now nowadays we have more and more storage and you have more and more load that you can shift in time. So this for active power is very coupled and will be more and more coupled. For reactive power, you can basically decouple. It's they respond quasi instantaneously, which is amazing, and also simplifies quite a lot our planning problem because you can naturally decompose without really doing very, very sophisticated maths. So that was, let's say, the nice point. Okay, methodology. Sorry, again, it's very long. I will go very quick through it. If you are interested, just go to the paper, and if you have a further question, contact me. So input of the methodology is exactly what I presented so far. So it's the methodology that serves to see when to identify the breakpoint of reactive power scarcity, so to have some hotspots already, some weak points in the system, and also to see if it's a problem of absorption or of reactive power or production of reactive power. Okay, so you have some candidate location already from applying the previous methodology. Then obviously you get the same input data, like you have in the VAR planning, whatever you want in the energy transition, penetration of renewables, load profiles, contingency, obviously, and well, some scenarios, for each of them. And then basically you need to come up with some, we call here is tuple. So tuple, it's a combination of an uncertainty scenario, so like realization of renewable energy production at different nodes and different power plants, a time of the day, and a contingency, basically a system, electric system state, normal operation or contingency. Okay, so we start by solving these multi-periods, and basically we try to come up to identify in the whole methodology what are the critical tuples. So let's say this combination that pose problem and need to be secure. So basically that iterations here serve to find out this. We have also some security assessment to check the tuples, but again, here is the control. Here is where you will reinforce. You will find out at which location and how much reactive power you need to install, so that to couple with to satisfy all scenario. And then at the end, obviously, you will come up as an outcome with optimal location, size, and type of technology that you could install. Something which is tricky here, it's also the discrete variables, because some of those, let's say, like shunt reactor banks or capacitor have discrete values. So again, it's more complicated in that perspective. You need to take into account of that, and we do that. Then something to say, what is different in VAR planning as compared to, let's say, generator expansion planning or transmission expansion and so on, is it that it's more agile in the sense that you don't need, like for transmission planning, to plan 20 years in ahead, because you need to construct lines, you need, I don't know how many permission. Here it's simpler in the sense that the TSO owns the substation, and basically you can do even years ahead or year ahead, 1 year ahead, and okay, I will buy this synchronous condenser, I will buy this shunt, or I will switch their place, and then I will install it, I will make some space in that substation. Basically, apparently in some countries substations are so crowded that you cannot afford, a new bus bar and a synchronous condenser being there. But okay, I think this is a bit, to some extent, it's more manageable from that, let's say, implementation perspective than issues with active power. Good. So we tested in this 60-node system again with blue here. It's the generators that we phased out. Some here with there are some candidate location where it's for condenser, for facts, condenser facts, reactors, synchronous condenser, and so on. So in general, biggest issues are here in the south in that system. Okay, where are the hotspots, let's say. Then we tested also different assumptions, just to highlight, I'm going to highlight the importance of each, because again, as you saw already for the previous methodology, assumptions have a lot of impact, may have a lot of impact on the results that you get out of it. So for instance, it was a type of control actions that you may have that could be preventive, so just before a contingency happen, but could be also both preventive and corrective. Here I have in bold things that change from one case to another. Here, for instance, refine limits. I mean that for synchronous machine and also for wind power plants and solar power plants, we go into very refined reactive power capability limits. It's not a simple limit, a physical hard limit, okay, like, which is the simplest assumption. Then for this one, I have type of technology, okay. In some cases, we have only reactors, capacitor. In another, we have synchronous condenser. We have SVCs or STATCOMs, okay. Then also discreteness of some of the variables, again, and the fact that you can have corrective actions. And obviously, the results are different in all of those cases. So the investment cost and CPU time I would call later. So we have first a direct approach. In that case, it was possible still, given that the size is not that big, to solve the problems, most of them to optimality. So these are the results for the cases, and you can see already that the invested costs are completely different in all cases. So it says again to what extent it is important that the operators, with the help of operators, we set this assumption properly. Because in one case you may see, okay, look here, I don't need to install anything. And why? Because in that case you have corrective action. So if you allow after a contingency, you say, okay, as a TSO, I still can do some to redispatch my some of the reactive power assets, then I don't need to invest. But if I want to work more conservatively, so I say, okay, whatever contingency I don't have the time to act and to do this redispatch, then you have some costs. What is important to notice is that our approach finds exactly the same optimum values, but it's much faster, okay, in all cases. So direct approach here, it takes half of the day, but for us, it takes much less, okay, and in general, it's very easy to do. Now, again, in all cases, when you look at the location, technology, and size of new sources, again, obviously, as the investment cost was different, it means that what you need to install is different. In most of the cases, capacitors were fine because there were low voltage issues. In that cases that we studied, and but in some cases it's better to have synchronous condenser. Okay, here also is the TSO who needs to understand the variability of it, because now we cannot control only with synchronous, with these old style devices like with discrete steps, everything. Okay, we need something which more continuous control. So these are just cases, again, to highlight the importance of hypothesis. This is very, very tricky from optimization, but I will skip it, that we have conflicting tuples you could find in the paper things. Let's go some details on numerical convergence and performance. So as I said, the 5 cases here, 1 to 5 in general, you do maximum 5 loops into the methodology. And again, for that system, have you seen that is quite easy. For the large case, we do 2 loops only. So large case is, again, this 1,200 nodes with 20 contingencies. Obviously, the direct approach, so if you formulate a problem and pass to a solver, cannot solve it because it's huge. So only our method managed to solve. But still, if you look here at the time, it's almost 9 hours, right? So, but again, in planning, you can do. So you can solve even larger system. This is not a problem. So some brief conclusions again. I think that this is a good methodology that could be used already or with some adjustment by TSO to plan and to understand where they could, let's say, reinforce the reactive power compensation in the transmission system. And that could be a good decision support tool for them in different time frames. But okay, it doesn't look like everything. So for instance, we don't look at voltage instability. So it's just static. So we need just to cope with voltage profiles. So voltage stability is something that comes after. And okay, it's better to have a look at this as well. Okay. Then, as I said, let's move to TSO-DSO coordination. I said that there are a lot of distributed energy resources in distribution system that can support. There is a paper that I like very much. I'm very proud of that here, coming out of our team. And we developed a 5-step coordination between TSO and DSO. I will go very fast. So basically what they need to agree on, it's at a substation interface, active power, reactive power, and voltage, okay? So first, the DSO would, but this is not only for voltage, it's for active and reactive power. So first, the DSO will calculate how much active power he can or she can provide at the interface with the DSO, but also at the same time at what cost. Then the TSO will run a security constraint OPF for congestion only if there is any congestion. So they may use some of the active power and then they will fix the active power flow at the interface, okay? Then the DSO for that agreed fixed active power flow at the interface will calculate how much reactive power they could provide to the transmission system and at what cost, okay? And then the TSO will run another security constraint OPF problem for procuring voltage, ancillary service to control voltages that may use some of the reactive power of the DSO. So basically, at that stage, they will fix reactive power and voltage at the interface. And then with these 3 values known, the DSO will solve an optimization problem and will distribute and will manage DERs on the distribution system such that to obviously to satisfy all voltage, all constraints in the distribution system, but also to keep up with these 3 settings. Okay, so you could have a look into the paper. Now from reactive power, so at an interface, we had in that case 5 interfaces. I'm showing only 5. So basically you would have this limit. So this with blue, it's the lower limit. So you don't see everything here. With red is the upper limit of reactive power at an interface. Then with this purple, you have the initial power flow and then the optimal one in green. Okay, so you can see that in general they took close to the lower bound from what I see in most cases. Obviously, they are variable in time depending on interface and so on and so forth. Okay, so again, you could have a look at the paper for more results. Then the issue is the cost. The cost is very important, and I worked on that. So if you look at a distribution system like inspired from Baran and Wu, you know, just for proof of concept with some solar and some batteries, some flexible loads, and and some wind power. So if I'm looking at how much it would cost to have reactive power injection or absorption here by the DSO through the TSO. So I developed in that letter published 2 years ago a methodology in which I come up with piecewise linear approximation. This is for a single period of time. Okay, so basically this would be the initial point, like zero cost, and then if the TSO would need to have, I don't know, 6 megawatt, then they need to pay that cost. If they need to have minus 2 megawatt there as deviation from the schedule, they will need to pay that cost. So these are very easy to embed in any tools for the TSO level. They are simply piecewise linear curves, okay? And this makes a difference. Then from that, I moved into a paper that was published recently this year, also in transactional power. No, it's not in transaction. This is in SIGAN. It was presented in IREP conferences. I take into account 24 hours period. So basically from the zero, which is zero is correspond to the current power flow. So I was starting adding, you know, saying that I increase in all periods of time with 1 megawatt the reactive power flow of the interface. I solve a multi-period optimal power flow and I come up with a cost. Then I keep increasing with 1 more megawatt, 1 more until you manage to go, and then I go the same thing. I reduce with 1 megawatt, 2 megawatt, 3, 4, whatever. So basically I calculate some cost then, and then it's very simple. You simply connect the dots, and by connecting the dots, you get this V-shape cost curves that could be easily integrated, okay, into the tools of the TSO. So these were, I think, the main features that could influence the way in which we are going to tackle volt-var problem, and we are going to design volt-var control. And this is based at the end, actually my last slide, about once you have all of this knowledge and all this complexity of the problem, I think also that the control of voltages through reactive power needs to be rethinked again, not from scratch, but significantly rethink, because again, here what I present are mainly prerequisite, okay, to have a better voltage support. Is not how you control in real time the voltage, but it's just how you get some better set points that you can send to the devices in the field to keep, okay. So prerequisite is that you need to have sufficient reactive power reserves, okay, to absorb and to produce reactive power at suitable locations. And I think the methodologies that I presented are very good to that extent. Then you may need to have a better granularity, as I said, in the control. So you may need synchronous condenser and statcoms that are able to better control voltages in a continuous range, not like what we have in the past, you know, capacitor and reactors that work by big discrete steps. Okay, with renewables, we need to have much more continuous controllability. Then again, IBRs in grid forming mode in transmission should regulate voltage set points that are sent by the TSO, which is not today. Today, they, you know, from own experience that, you know, they either operate at unitary power factor or at a given power factor, like depending on the active power production. Then it's very important that the distribution systems should contribute actively to support transmission system voltages. That's the different ways you can think about it, simply in an algorithm that I sent, but it could be also that they, for now, they would, for instance, stay in a 4-quadrant envelope and control active and reactive power flow at the interface in a 4-quadrant, for instance, or 1 quadrant, or whatever the DSO and TSO, given the progress in the energy transition, would deem useful. Something which is very important is that the voltage set points for voltage control now should be computed faster. So we really need the optimization and things that look ahead and in very shorter time frames, as you have a lot of variability from renewables. So you need to be, if you go into security constraint APF that you saw, you need to be very tractable, indeed tractable. and also to rethink secondary and tertiary voltage control. You know, probably some of you may heard that in the past, you know, Italy and France, for instance, they were used to have this secondary voltage control. And now the good thing, in the past it was quite boring, I would say, because as I said, everything was easy to predict and it was quite easy. No big issues with voltages. But now I really like to see that, and I noticed that RT France, for instance, they start rethinking secondary voltage control. So basically, they took it back and they rethink how this could be done, because it's very important with high penetration of renewables. So basically, with tertiary voltage control, you may calculate optimal set points for your reactive power assets like 1 hour ahead. With secondary, you would have to see like every 10-15 minutes ahead, okay? So in some specific pilot nodes, how to control voltages, okay? And obviously, we need to consider voltage stability constraints based on it. It's not only, you know, the voltage by itself, that it's not the voltage magnitude at a certain location is not a good indicator of the proximity to voltage instability. So yeah, this is something we need to think about. So I think that this concludes my presentation, and look forward to your question. Thank you very much.
Thanks a lot, Florin, for the presentation. So any questions from the audience? Okay, okay, no questions. So, quite interesting presentation, Florin, because at the end of the day, we cannot forget the fundamentals. We need reactive power to transmit active power. And it is really nice. Probably today, everybody is looking at the grid former converters, inertia, how to provide primary frequency regulation and so forth. But classical volt-var problem and classical reactive power problems are still there, and we need to solve them. So at the very beginning of your presentation, you said that the quality of the reactive power provided by renewable energy sources is not as good as, let's say, synchronous generator. I do not fully agree with this, because at the end of the day, you know, a voltage converter as an interface of a PV power plant or something like that has almost the exact model than a synchronous generator. And at the end of the day, it can do this reactive power provision. Probably it's much more difficult because in the case of a large power plant, you may have only a single unit that it is quite easy to control. But in the case of a large PV plant, you have several PV inverters that you have to coordinate with a power plant controller. It is much more difficult, but I think that from the point of view of the quality of providing this reactive power to the system, it can be exactly the same. More tricky, but exactly the same. I would like your opinion on this.
Yeah, thanks a lot for the question. I agree that they could do, power electronics can do amazing things. I mean, the main issue regarding the technology itself is that they were designed, the converters, I mean, basically with the mindset to produce only active power. For that reason, as I said, the biggest issue is if you take the same rated power, so MVA, you look into a synchronous generator, how much it can produce or absorb reactive power based on this MVA. You can find, like, for instance, in active production, they could go to 80% of the capacity. In absorption, they could go maybe to 60%. Well, if you look at converters, as I said, because they are already in the field, and at the beginning, they were meant only to produce active power. So you can see that in absorption, they are only 20%. So you see, that's the difference. And in production, they can go to 60%. I mean, they are amazing. They can do very fast, and you can do plenty of amazing things with it. But physically, it's, you know, the amount of reactive power they can produce is smaller, much smaller than with a synchronous generator. That was my, let's say, my main point of
But at the end of the day, it is a matter of design, because I mean, voltage converters may provide zero power factor if you want. The only thing that you have to do is to coordinate how to rate the DC bus with the coupling filter, and that's it. So it is a matter of design, and probably the PV inverter manufacturers doing that way because there is not a clear requirement from the
Exactly.
codes.
So as I said,
Exactly.
I fully agree with you. I fully agree with you, but in some locations, so indeed, it was not a requirement. They didn't care about that. They could have even not have at all, you know, but they knew that at some point they may be asked to control voltages at the point of common coupling. But those that are in the field cannot do better than what they have, right? And they will stay there for tens of years, right? So, but the new generations, maybe they can be designed like oversizing a bit the converter in one way or another to have larger capabilities. Especially, as I said, those who may be at critical locations, like if they are in a, I don't know, close to big load center. Again, it's very important to have more reactive power capability by design. But as I said, if they are somewhere in the North Sea, very far from whatever load at 200, 300 kilometers, you know, from a big load, they may have infinite. So you can oversize your converter as much as you can. This reactive power will not serve much, you see. So that was my point. So again, it's the design, and I'm not sure that the time that the people will realize, okay, in this case, we will need more converters or so on, but okay, they can and should provide reactive power support and control voltages. And I think this is in the future. But still, the operators, I think that's the tricky point. There should be probably a hybrid approach. I think it would be best in which the transmission system operator really invest themselves into some reactive power compensation, not waiting only for, you know, power converters to support the grid. So, but what is, let's say, the right trade-off? Again, it's a matter of optimization, and it's not very easy to respond. But I'm fully in favor, like you see, in some TSO, as I mentioned, especially in Italy, they invest into synchronous condensers. And as I said, this is amazing. You know, they control pretty much three things, which is great. You know, when you move into something where you integrate, you know, volatile renewable energy sources into the grid.
Yeah, the other comment that it is interesting from your presentation is the situation of high voltages that require absorption of reactive power. That not was the case in the old days. So yeah. I think that in the future we will need to install probably lots of probably reactors at the subtransmissions and distribution levels, because a lot of generation is going to be installed over there.
Yeah, exactly. I fully agree. So again, in the past, as I said, there were always the peak load that posed problem from everything, you know, from thermal overloading of equipments to low voltages. Today, you know, we have this, you know, midday in Europe in summer, where is plenty of solar production pretty much everywhere. The voltages are very high. You know, there are no conventional generators, basically, or very few connected, you know, because, you know, all these renewables have to provide, you know, so they are displaced from the game. And indeed, the voltages get up. I know from other countries as well, it happens, and it starts happening, you know, the absorption, it's getting worse, especially in the, you know, middle of the day, you know. And well, I think that's very, very important to have appropriate absorption capability in the system.
You have also commented the importance that today have synchronous condensers. So yeah, you said that synchronous condensers are the silver bullet because they provide may contribute to the voltage regulation. They provide inertia, and at the same time they can contribute on the short circuit power. But yeah, I fully agree with this. But on the other hand, our silver bullet is a technology of the past century. So we are now integrating a lot of renewables with power electronics and so forth, but we are still relying on our, let's say, electrical rotating machine. So my question is, why not thinking about a power electronic solution? A STATCOM with extended capabilities. I mean, a STATCOM with a little bit of energy storage in the DC bus can provide these inertial resources, And probably also if we think about some kind of overrating of the power electronic stack, may provide also not large short circuit current, but probably a modest one, I would say, 2 per unit. I think that we need to rethink about this assumption of installing more synchronous condenser. Maybe it could be done in another alternative manner. What do you think about that?
Yeah, very interesting point. So again, I think that I don't have the let's say a cost, how much it costs each technology, for instance. I don't have any idea. I think that operators are in a best position to judge, the cost of one versus the another. I think that indeed what you mentioned, it's clear that, you can oversize converters and they could do a little bit better, in providing current. But again, the cost increases in the design, and it could be used, as you mentioned, STATCOMs to do that. I think it's a matter of cost and technology, right? And I cannot have an answer as long as I don't know exactly how the costs are. So I would say, like, to be careful, I would say, and cautious. That could be a hybrid, in which you may use some synchronous condenser, but you may also use some STATCOMs, So it's a matter of preference, okay, at the end of the day. But I wouldn't go into fully STATCOMs or fully using, IBRs is better. I think, like in life, like in everything, to have a diverse portfolio, right, of solutions. Sure. Because if some fails at some point, you may still have the others to compensate, right?
Yeah, perfect. So any other questions from the audience? So thanks a lot, Florin, for your interesting talk. Thanks a lot.
Yeah, thank you very much for the invitation, and have a nice day all.